So far, we have investigated the cause of the compressor curve, that is, the method in which head is produced in any impeller. Recall, head is produced by the change in two velocities, namely the difference between inlet and discharge velocity relative to the blade, and the change between inlet blade tip speed and discharge blade tip speed. In this section, we will explore what will happen to the energy production or head production of an impeller if that impeller were to change in area. Therefore, we will explain the mechanism of impeller fouling with examples of the effect of fouling at the operating point and discuss measures to prevent and correct fouling. As already discussed in a previous video, you can reduce any blade row or impeller to a series of equivalent orifices, as depicted in this example. Recall that flow is a function of area and velocity. Whenever any blade row or impeller is designed, the designer sets inlet and discharge blade areas such that optimum velocities relative to the blade will be achieved at each location. By a series of tests and experience, designers have defined optimum relative velocity rather well. Therefore, the resulting inlet and discharge areas will produce optimum velocities and corresponding optimum impeller efficiencies. If, however, the areas were to change and flow passages were to become rough and non-continuous, an impeller performance change would result. Now, take a look at the following figure. It presents how a fouled impeller would look like. On the left side, a side view of the impeller with fouling. On the right side, the same fouled impeller is presented, but only the upper half of it, with the side plate removed. And here you can see the fouling across the impeller blades. Impeller fouling is defined as the accumulation of debris in the impeller or blade passages that reduces the flow area and roughens the surface finish. The distribution of the foulant on the impeller or blade row is non-uniform and usually changes with time. Flow patterns within the impeller or blade cause unequal distribution. In addition, the forces exerted on the foulant cause it to chip off with time as it becomes dry and brittle. This results in a change in rotor balance and a change in performance of the compressor, as we will see in a later video. To understand the effect of fouling, let's refer back to the previous example of a backward-leaning centrifugal compressor impeller. Here, the impeller is clean. You can see the gas velocity relative to the blade, and here the blade tip speed in clean conditions. The gas exit velocity is the sum of these two vectors, as depicted here, with its corresponding flow angle. Let's call it alpha C, where C refers to the clean conditions. When the impeller becomes fouled, as seen here, the area of the flow passage is reduced. Since the gas flow is equal to the product of the area and the gas velocity, then a decreasing area will result in an increasing velocity for a given flow. This is illustrated here in red with the vector V relative fouled. In this case, the gas exit velocity will be as follows, with its corresponding flow angle alpha F, where F refers to the fouled conditions. Now let's get rid of the vectors U, V relative clean and V relative fouled, as we don't need them anymore for the discussion that follows, and leave only R clean and R fouled. Let's now plot on this graph the x-component or tangential velocity for these two vectors. As you can see here, the increase in the flow angle and the gas exit velocity due to the fouling has reduced the tangential velocity of the gas. You can see here that the tangential velocity of the gas in the fouled condition is lower than that in the clean condition. Now, since the head or energy produced by the impeller is the product of the impeller tip speed, which does not change in the fouled condition, and the tangential velocity, which is reduced, then the head produced will be reduced in the fouled condition. In addition, the non-uniform distribution of the foulant will reduce the efficiency of the impeller stage. Let's have a closer look. Here you can see the side view of a clean impeller with its corresponding performance curve, namely the head capacity curve and the efficiency curve, as well as the impeller design point and low flow limit or surge limit. Now, impeller fouling is the accumulation of material in the impeller passages, as depicted here. This will reduce flow area and roughen surface finish. It will also reduce impeller head capacity and efficiency, as depicted in this graph. Note here that the surge margin actually increases slightly in the fouled condition. This is because the cause of surge is low gas velocity. Since the area of the flow passage is reduced, then the gas velocity increases, thus increasing the surge margin. The surge margin is defined as the flow at surge divided by the impeller design flow. However, the stage head produced by the impeller at any flow rate is reduced. Therefore, for the same process system head required as depicted in this example, the impeller flow rate will be reduced from the design point to the fouled flow, thus forcing the operating point closer and closer to the surge line. Fouling is difficult to predict. In air services, it is a function of the environment which can change with time. Fouling of an air compressor or the air compressor section of a gas turbine can suddenly occur. Causes could be a new industrial plant in the area, a new furnace stack in the area, change in prevailing wind direction, or land erosion caused by deforestation. In process applications, fouling can also occur unannounced. One example that comes to mind is a polyethylene plant recycle compressor in which I participated. A new 30% larger recycle compressor was installed, and immediately after startup, the entire compressor was fouled with fines and polyethylene resins. The previous recycle compressor had not fouled in 10 years of operation. The following figure will show you the removed rotor after only 1 week of operation. Here you can see a front view of the impeller showing the blades and the impeller eye. You can see the fine deposits on the blades reducing the gas passage. Here the fouled impeller is seen from another angle. And here a closer look to show you that even the impeller eye seal was fouled. And here you can see the rotor during disassembly with the impeller on one side and the shaft bearing a mechanical seal on the other side. So what was the root cause? Well, after an exhaustive troubleshooting period, it was discovered that one of the filters upstream the compressor was not performing its duty, and the polyethylene fines were not entirely retained and were carried over to the compressor section along with hydrocarbons. Redesign of the filters solved the problem. In other chemical processes, a slight change in operating conditions can cause polymers to be formed that will stick firmly to the impeller passages. As an example, polymerization can occur in ethylene plant cracked gas compressors, as depicted here. They can also occur in linear low-density polyethylene recycled compressors. In these services, the temperature of the process gas within the compressor must be kept below the critical temperature that will initiate the formation of polymers. This temperature varies with the process and should be in general below 235 degrees Fahrenheit to avoid problems. Now, as we have learned in previous sections, process gas temperature change within any compressor is a function of compressor efficiency. Therefore, compressor stage efficiency deterioration due to excessive stage seal clearances, impeller erosion or axial misalignment can initiate fouling in these processes. Most centrifugal and all axial compressors have more than one stage, as it is the case for this centrifugal multi-stage vertically split compressor. Fouling can occur in all stages, only the first stage, or in any combination. The overall effect of fouling on compressor performance will be the accumulative effect of deterioration in each stage. The following figure shows an example of fouling in the first and second stage of a three-stage centrifugal compressor, as well as the impact of fouling on the overall section performance. Now, since fouling is extremely difficult to predict, then I strongly advise you to establish a sort of a periodic condition monitoring of your compressor performance. This can provide advance warning to correct compressor internal deficiencies at the first opportunity. As discussed in a previous video, the mechanism of fouling involves non-uniform accumulation and removal of debris from the impeller or blade row, which results in a performance design change in the mass accumulation of the foulant on the impeller. This action will change the rotor balance and the phase angle of the imbalance. Now, to detect and confirm the fouling, I strongly advise you to proceed as follows. First, trend radial vibration and phase angle. A random change in both parameters indicates fouling. You can also trend compressor head and efficiency, then plot results on compressor test curve. An increasing deficiency margin confirms fouling. Up to this point, we have seen how fouling can occur and how it can cause surge. The detrimental effects of surge have been discussed in a previous video. How then can we prevent fouling if possible? And how can we correct fouling if and when it occurs? Can we correct fouling online? These are important questions that must be answered. The discussion that follows will present solutions for preventing and correcting fouling. Let's begin with preventive measures. First, we'll list them, then we'll see each one in details. Preventive measures include process control, proper inlet air filter selection and maintenance, condition monitoring for pressure, temperature and vibration, online solvent injection, and impeller or blade coatings. Corrective measures include slow roll or stationary wash, and online random washing. Let's begin first by examining in details the preventive measures listed here. What I will describe for you now are proven methods for preventing fouling, so this part of the video may be very useful for you. First thing to remember and keep in mind is that accurate control of process conditions can prevent fouling in application where polymers can be formed. Control of temperature is usually the most important. If you do work in a refinery or a petrochemical plant, then the following applications can be affected by excessive process temperature: ethylene cracked gas, linear low-density polyethylene, high-density polypropylene, fluid catalytic cracker of gas, thermal catalytic cracker of gas, and coker gas. The temperature below which fouling can be prevented varies with each process, compressor, and application. Monitoring of process conditions is necessary to establish a threshold temperature in each case. In some cases, however, fouling cannot be prevented with the existing compressor. It may be necessary to modify the aerodynamic design or add additional cooling. Note that water injection is used quite regularly in ethylene unit cracked gas compressors to reduce gas temperature. However, an industry standard or best practice is to keep the amount of injection water below 3% of the inlet mass flow. The second effective preventive measure includes proper selection and maintenance of inlet filter. In air compressor and gas turbine applications, filter selection is an important factor in preventing fouling. Site conditions must be accurately monitored prior to any installation. So, I strongly advise you to contact your local filter vendors to survey your site conditions. Recall that filters must be able to prevent debris from entering your compressor. In platform applications and installation close to water, special designs must be used to prevent excessive chloride buildup. For this, my advice to you is to consider multi-stage air filtration. Another important consideration is filter maintainability. For crucial services, filters with online cleaning capability should be considered. Be aware, though, that in recent years, pulse-type filters that use a reverse air pulse to clean filter cartridges when filter pressure drop becomes excessive have become quite popular in the industry. Finally, regardless of the type of air filtration used or not used, remember that environmental conditions can change as previously discussed in the beginning of this section. The next preventive measure that we will cover is the accurate condition monitoring of compressor parameters. Regardless of the service, condition monitoring of molecular weight, pressure, and temperature will provide valuable information regarding process condition changes that can cause or increase fouling. Online solvent injection is another effective preventive measure. Certain process applications have had success with this method. The objective of this measure is to continuously inject a small amount of solvent to reduce the friction coefficient of the blade and impeller surface and thus prevent the fouling from accumulating on the surface. The object of solvent injection is often misunderstood. The idea here is to prevent foulant accumulation, not clean the impeller or blade online. Non-continuous solvent injection will allow the impeller or blade surface to dry and thus will promote fouling. Even if a unit injection is continuous, selection and location of injection spray nozzles is a critical factor in success. Insertion of spray nozzles in the inlet pipe of the compressor section is usually not as effective as injection directly into each stage of the compressor. Knowledge of solvent vapor pressure and internal compressor temperatures is necessary to determine if section or stage solvent injection is required. Type of spray nozzle to be used can best be determined by discussions with process designers or other users having similar process applications. Now, of course, there is no question about it. Solvent injection is quite expensive. Many users have required flow meters at each injection point to determine the proper amount of injection. Typically, the total amount of solvent injection in one compressor case should be 1 to 2% of mass flow. An industry best practice is that the total amount should never exceed 3% of weight flow. Excessive solvent injection will erode blade tips and can cause impeller failure if not detected in time. The last preventive measure that we will cover in this video is impeller or blade coatings. In the last couple of years, some users have investigated and have used impeller and blade coatings to reduce friction, instead of continuous solvent injection. In my professional experience, this has met with mixed results. There has been, however, success with coating impellers with Teflon-based material in ethylene-cracked gas services. So, for this last measure, I recommend that you talk with your process designer and ask your compressor vendor for additional information. Let's now shift our attention to corrective measures. If fouling cannot be immediately prevented, various offline and online cleaning methods are available. Offline cleaning methods are definitely preferred to online cleaning methods, since they do not expose the compressor to vibration excursions and have proven to be more effective if a compressor is severely fouled. Failure to immediately remove all foulant from the rotor can cause catastrophic failure, since a large amount of imbalance can be instantaneously introduced in the rotor system. General guidelines for an offline cleaning method are presented here. Now, if an online cleaning is to be used, then it should be employed periodically. The industry best practice is to do it at least once a week, and it should begin when the rotor is in the new clean condition. As described previously, the injected amount of wash fluid should not exceed 3% of mass flow. Process and compressor designers should be consulted regarding the exact procedure to be used. However, I strongly advise you to use a radial vibration trip system if online cleaning methods is to be implemented. This action will prevent catastrophic compressor failure in the event of an incomplete online cleaning. Finally, to finish off this video, I have included some examples of fouling along with preventive measures and cleaning methods in the following table.